Oh, it's recorded.
Yes, yes.
I didn't do my makeup.
It's
Hey, Michael.
just the screen actually that's recorded. So, okay.
Hallo Michael. Wie geht's?
Can we hear
Hi.
you? Yeah.
I'm participating in a conference. Still have doing my final tweaks on my PowerPoint presentation for tomorrow. It still feels like Lisbon is like years away, but I see you are already there.
And it's nice here. Hi. I don't think you see. Yeah.
I don't think he's looking at the screen.
Yeah.
No.
Yeah.
Adrian was waving at you. So is this the slides,
Maybe he
Thomas?
was, but he doesn't hear.
Am I in the slides?
So if you move the mouse to the right side,
This right side?
so outside of the screen,
Ah,
to that screen.
That makes sense. Right. Okay, guys.
Okay, let's go. Aliona is not there yet.
Jan, are you joining? I think that's a no.
Yeah, go ahead.
So are we gonna call it Apple?
I'm
Yeah,
not sure.
it's-
Do you think we'll be able to? Like, if I play the role of Ravin,
Oh yeah, exactly.
guys, I don't think it's gonna fly with Apple's
They cannot have
army
the
of lawyers.
They cannot have the
You don't want to take the risk, Ricardo.
Apple.
These
Yeah.
guys are crazy.
That's true.
as long as we don't use an apple in the logo, should be
You
fine.
just say
Yeah.
it's Apple, not Apple.
It's Apple.
Yeah. Or we just say it's APPL.
No. Apple.
Yeah, no, I
APPL.
do Apple, but we don't use an apple as the logo.
No, it's red, so it's fine.
Yeah.
But like actually the E, like we should cut a bit there, no? Like
I mean, they did not trademark apples, I think.
You'd be surprised.
I think
They
they
run
try
the
to
brand.
trademark everything.
Yeah.
no more apples.
Yeah.
Right, guys. So this is just a reason why we moved to Apple a bit, or why we decided to go. So this is V3, and this is how variables kind of work or distributions. You create a PM normal, and you get this weird thing called a free random variable.
Yeah.
If you look under the hood, it's a tensor variable, but it's like bare bones. It has nothing to it. You know, it doesn't have an owner, doesn't have any inputs to it, no outputs. We don't know where this goes.
Ricardo, can I interrupt?
Yeah.
In a sec, Mina is asking if the call is still on.
Sure.
Ah, yeah.
So maybe she tried to join the Google Meet.
But there's a late fee.
Huh. That's weird. We should see.
Did you share the meet link?
No.
Maybe she just asked if it's still on.
I always get confused between dot and tensor dot. That should be a talk.
I don't know what's the difference.
Oh.
Is
Yeah,
one
exactly.
like
I never know what the difference is between tensor dot and dot.
I mean, dot is a tensor dot.
Yeah, but dot I can use. Tensor dot I always mix it up.
maybe it has different args.
Yeah.
Different everything.
So it acts like a tensor variable, but it's not.
It is a tensor variable, but it's like a raw,
It doesn't
yeah.
act like it.
Yeah.
Yeah, like
And
you
the-
can do anything with
Yeah,
that.
and if you have a I y equals PM normal that's based on X, there's no relationship between the two. Like
Yeah.
for us as a user, like obviously they are connected in the graph.
Internally somewhere in the input and
Yeah.
owner and stuff. It is
Yeah,
somewhere
yeah,
like
yeah.
that.
Yeah.
It's
Otherwise
not
it wouldn't
really
work.
graph, I think.
Exactly. So we just
So
yeah.
it's
So I think the only thing we are taking from here is basically we plug a graph and then we can get derivatives and stuff like that, but we're not using any other feature of
Yeah.
Tiano
Lots
or
of
SR.
waiting
Now you
power.
need to accept her.
Hello, Osvaldo.
You need to first accept. I
Oh.
think.
Admit.
But I can deny.
And we can leave the room.
Hello.
Hey, Osvaldo.
Hello.
Hello.
Hello, or should I say hola?
Hola.
¿Qué tal?
I'm actually
Muy bien.
here. Hello.
Hi.
So I was just starting and giving it. Okay, this is our unofficial logo. Let me go back.
You need to
That's
move
very
the mouse
important.
To the right side. All the way. Yeah, there you
Okay, our unofficial logo. Yeah, we are thinking about the copyright issues, but that will come for discussion. So I was just saying in V3 our variables and distributions work where you call this, x equals PM normal, and you get this object that's a free random variable, which is just masquerading. It's basically a tensor variable, but doesn't have much more to it. So like we don't know what the inputs are to this tensor variable. We don't know where it goes. So we have a very crude, Tiano tensor variable, and this is V3. In V4, very good plot. In V4, things work a bit differently. So we call x equals. Wait, do I have the laser pointer?
Yeah.
Oh my god, the resolution of this thing is insane. I need binoculars. Laser point, or L. Okay. All right, yeah.
It's 8K or something?
Yeah,
Like
8K.
Okay, so that's why it was super small.
Right, so we call still a PM normal. Now there was some printing added. It's still a tensor variable, but now we have an owner, which means basically we know what are the inputs to this, and it's this weird thing, which is basically the inputs of a random variable. So random variable, for those who don't know, first argument is always a shared random state, right, which is used for the random generator. Mm-hmm. Second argument is the size, which in this case is none, so it's just an empty list. Third one is just a code for the output type, so in this case it's a float 64, it is given a number 11. Right, and the other two are the ones that are interested. They are the arguments, so 0 is the mean, 1 is the scale. Right, so we know what are the inputs, and obviously if you have nested variables, you're going to know, the mean of this normal can be y or something like that. You can also call xeval, so it just works as a random number generator. Mm-hmm. Okay. And what we do, so line 2, so this snippet is how you call a normal, but I'm just going to show a bit of what's happening on the back end, just so that we understand what Apple is going to do later. So you can actually get the same result in a model with a normal if you just create ISR a random normal that's completely non-PyMC, right? You just create an X, and then you just say register this in the model and give it a name X. Mm-hmm. Okay, so this is the magic behind the curtain of, basically registers some things in the backend that then we can use. But you could just create all the random variables outside of a model context and then just say register this in the model, in this order.
And register RV is new in V4?
Yeah.
Okay, so that's a new.
I think it's new. Might exist for something else, but
okay.
No, it probably existed. So it's what creates this value variable. I'll come back to it, and it says this value variable is related to this random variable.
Okay, so then when you instantiate PM.normal, it looks for the context model.
So what PM normal does at the end is calls model register RV and returns the result of that, which is just the X again. So this second line happens if you just call PM.normal with the name. Yeah. Couple more things in between with shape handling and stuff, but you can do it manually like this. So now we registered, it appears as in the free random variables, and also there is this dictionary that maps random variables to value variables, and here we have X. This is the RV is mapping to the value variable. Okay. If we call dist, just
about the value variable, is there an equivalent in V3 to the value variable?
There is not an equivalent to the random, but the value variable is what we had in V3. Basically, that empty tensor variable that had no connections to anything.
So that's the value variable?
I think so.
Okay.
Are you going to explain what the value is?
Yeah, sure. Where do I explain it? I'll explain
that yet?
For me, it was also very non-intuitive. What the hell is this variable? I think
in
in the next slide.
Yeah.
So I just have an aside here. What does the dot dist do nowadays? Mm-hmm. The dot dist is just a wrapper. It says basically what this dot dist is doing is just this first line is exactly the same as the first line here. Okay. It's just returning a random variable, but it's not registering in the model. It's not doing any model-related stuff.
That's actually kind of cool.
And we have it because we have, for instance, alternative parameterizations. And in ISR, you only have one way of defining any random variable, right? You cannot define in terms of tau. You can put mu sigma, But in PyMC3, we allow, for instance, tau. So what we do in the .dist is, if someone gives the tau, I convert it to sigma, and I instantiate the random normal with sigma instead of tau.
Nice.
Yeah. The mouse also moves. It takes a lot to move all these pixels. Right, Minal is joining. Hello. I guess she's there. Yeah. So .dist is just a wrapper that returns the random normal. So this line of code is doing exactly what before was happening. Okay. Yeah. Right.
Okay, so it's like it replaces.
So it's
the role
doing
of the SRI random normal.
Yeah, it has.
How does it work with transformed variables then?
Go there. So
Okay, next step.
yeah. No, we I don't have a slide, but what we are doing with transforms right now is we just let's see, where was I? Right. So this x that's returned, whatever this x, we are saving in the tag. For now, we are just saying this variable is going to be log transformed, okay? And then the information is just carried through the tag of this random variable. Okay.
And does that mean then that
we don't do anything about the value variable just yet. The only thing we say is this is going to want a log transform later on. Okay.
Okay.
So you just remember it.
Yeah. Probably we'll put it in a dictionary later. We're not going to use the tag anymore.
That's what I was going to say. So that means that probably we can save that in the trace afterwards, right?
Actually, I can show how we are doing it in Apple, which is, I think, a very clean way.
Okay, because then that's often something that's useful. Like, for instance, with RVs, if we could have that, like the transform associated to each variable, so that when you debug and you want the variables to look at the variables on the unconstrained or constrained space, you can switch with these transforms.
So I'll show. Then I'll go to the code and actually show an example how we use it in Apple. But basically, you have a mapping.
Yeah, exactly.
Value variable A, give this transform. Value variable B, give this transform.
And then to have that in the inference data object.
Yeah. So what's happening with transforms here? I think we might also. No, not yet. Yeah. So when we create the log P graph, then we do the transformation, and we also create this deterministic, which is the back transformation of the value variable, right? But that was the same in V3.
So transformations have to be one-on-one then.
No.
You can't have injective.
Like.
So, for example, if you had a distribution on angles.
Sure.
And just angles, you might want to have it internally as a 2D.
You can.
So the
value variable that you use as input does not have to have the same dimensionality, right? Because we're going to transform it before we pass it to the log P, and then just add the Jacobian term. Okay. So yeah, and we have the stick breaking does not have the same dimensionality. The input is not the same as if you're just calling the log P without the transform. But that has not changed. That's the same as in V3, right? Okay. Oops. Where is the mouse? All right. So yeah, .dist is just a wrapper then for just returning a ISR random variable. So about the log P, that's what we are doing different. So now you don't have any more, pm.normal.logp. That doesn't exist anymore. So what we do, and here is where the value comes. So let me go by order. So create a normal distribution. If you call eval, it's just a random variable.
Random draw.
A
random draw. A random draw from the distribution.
Yeah. Random draw. As if you called x.random, right? Or So the core objects now are the random objects, which before we are attaching it, kind of. Yeah.
Touching it?
We are kind of plugging it in. We are calling, normal.random, and then we had all these draw values, logic, everything. Right. So they are the building blocks of V4. It's basically the random methods are the building blocks of V4.
Nice.
What we still attach.
Different value every time. It's not.
Yeah. Okay. There is some magic happening.
The random state.
So we have an auto update going on.
Mm-hmm.
So a random variable, when you call a random variable, actually has two outputs. One output is the random draw, is the second output, the main output, and the first output is the next state of the random state.
Okay.
And then we just feed it. We say, the random state is now what came out of it. Right. So then So when I called PM normal, that line, the line I showed you before, the m.register happened, right? And it created this value variable. And the value variable in this case is just a tensor variable that has the same kind of generic shape as the random variable. So if it was a 2D tensor, it's going to be a 2D tensor.
Yeah.
It's going to have the same broadcastable. That's about it. And the PyMC model now has this mapping of random variables to values. So you can put the x and you get the respective value variable.
Mm-hmm.
Okay.
So what's the value of it?
Value variable. So the value variable is when you call, for instance, in a SciPy, when you have the normal distribution and you call the log PDF, you put 3 inputs, right? You put x, mu, and sigma. X is the value variable, right? Is where in the distribution are you evaluating the density?
Okay, so and x value is then, I guess, also a tensor variable? Or?
Yeah.
Okay.
Right. So, yeah. So we get the x value, and now to get the log p, we are using this dispatching trick where we basically, so we are calling pm log p, that's the user interface, or you can just say, I went for x, and the x value is the new input you have to give. And what's happening behind is looking x, what kind of variable is this? Is a random variable. What kind of random variable is it? It's a normal variable, so it finds the normal log p, which has 3 inputs, x, or value, mu, and sigma, right? And then it's giving you the function back that takes as input the mu and sigma from the original distribution, so 0, 1 in this case, and the new x value as the first argument. Where are you evaluating it?
Could I also at the log p level specify 0 and 1, or
no?
Value variable?
It's done in a way that always takes the arguments as the inputs automatically. The only thing you can specify is the value variable. And now you can evaluate it, right? Log p is just a symbolic expression. You could make it a function, or you can just call value and say x value is going to be 0. What is the log p? If the mu and sigma were symbolic, then you would also have to pass mu and sigma, right? So that's how log p is working.
Yeah, I'm curious about the details of the dispatch. That's
okay. That we can. Yeah, it's like 2 lines in source code. It's just using the func tools dispatch. So you just need to give x owner.op, and that's going to be in this case normal random variable, and that's it. Then he knows for this you want.
Okay, but so can I still say something if I want to provide log p implementations and say I have some transform variable?
So the transform happens all in the value variable, right? The transform does not affect the log p. In theory, like in the simplest cases.
Okay, but let's say I have a distribution where it's very easy to compute the log p in the transform space or in some transform space, but then not in the untransformed.
Then you need to implement your log p, and then you dispatch it on a new kind of random variable. You can inherit from, the normal random variable, and say this is going to be my fancy normal random variable, yeah. And then you dispatch your log p on that kind of variable, so that he knows when he finds it in a model to give this specific log p.
Okay, no, yeah.
But we can look at code later.
So the RSR graph that's generated is always just with random variables.
Yeah.
And then from there I can derive log p graph.
Yeah. Which in V3, in V4, the only thing is really going at each random variable and replacing it by what used to be the .log p in V3, right?
Interesting. Yeah.
Nothing fancy is happening here at this point yet.
And so we're just creating a new graph based on the old graph.
Yeah, we're basically going to every random variable and replacing it by, we extract the log p and then we just add up all the log p's, and this will be our log p graph.
Yeah, so we're copying, we're copying and changing.
Yeah, and replacing everything where we had, everything that depended on x is now going to depend on x value, because that's our input, right? There's not going to be a random x anymore in our final log p graph. So we have to look at all the distributions below that used x in some of the arguments and replace by x value. Yeah. So, so we get the log p, we evaluate it. We can also do this manually without going through a PyMC model at all, right? We create a random normal, we create a value manually instead of relying on the register RV. And then we call the log p with the 2, and we get exactly the same graph, right? So you just have an idea of how the things are working behind. yeah, at this point, except for some custom distributions that at this point we could do everything we do in V3 and V4 if we wanted. We would just have to create a custom random variable for every kind of distribution and say for this random variable use this log p, which is fine for normal distributions, but for things like mixtures it's a bit annoying that you would create a random variable for mixtures, right? Because mixtures are basically composite of other random variables. You don't want to create an OP just for, a mixture. So that will be where Apple comes, but before that, so this is just another motivating example for why we went to Apple is, what if we want to do something like this? You couldn't do in V3. Okay, this is kind of, let's say X is a deterministic, that's a normal distribution plus 1. And now I want the value variable to work on this X plus 1. So it says, I want the log P of this deterministic transformation of the normal. You couldn't do it in V3 and you cannot do it in V4 either at this point. But should be very easy, right? The only thing you should have to do in the backend is just say, I want the value, I just subtract 1 from the X value and then give me the log P you would give otherwise.
It's easy for +1, but right?
Yeah.
If you do more complicated things, then it's not easy.
Yeah, you need to add, but it's something that's not incredibly difficult. We're going to do this. So for monotonic transformations, you just have to add the Jacobian term and do the inverse transform of the value variable. So it's very straightforward, right? Now we know you are calling...
Let's say you're squaring it.
Sure. Squaring, no, because that's not monotonic. You could do it, but you would have to break it in a mixture, right? Negative and positive. You could, but let's say that we only have to implement what we want.
If it's... Okay, maybe let's...
You know what, now you have a graph, no? You know what operations are working on everything. You know that X is an addition, X is an addition between a constant and a random variable.
But for example, then you have to be able to prove that your transform is monotonic.
An addition with a constant has to be monotonic, right?
Yeah, of course, in special cases, that's easy, right?
So the way we are doing is we are implementing by hand. So we only implement the transformations we want. We are not saying find a general inverse. We're just saying, okay,
so you basically have special code for saying if you add something, you can do that.
If you have a multiplication, if you have exponentiation, we do it manually. Okay. Otherwise, give an error saying this kind of transformation is not implemented yet. Yeah. Okay. Because not everything is straightforward, or some So we are doing it the safe way. Okay, so in theory, we could do this. And I actually started a PR some time ago in V4 that was basically, this was working code at that point. We had a location, a scale, and now I had an X, which I wanted to be my random variable and value variable. I want my model to be defined in terms of X, which is just a fine transformation of a 0-1 normal distribution by log and scale. Okay? And then, manually I would just register the X, and this would be my only log P term would be this X. There would be no... log and scale would also have. Right, so that was working. So I could call the log P, and I was getting the right log P, which is exactly equivalent as if I had the normal with log and scale. Okay. So the idea is, now that we have everything is graphs, we can go a bit further than before, and we can derive some simple random variables and the log P for them. But things are not so simple. For instance, if you just, if you have a difference in sizes, you're going to have a graph that's going to have a broadcasting, right? So now your graph is not a multiplication between a random variable and, in this case, it's just multiplication, right? And another. It actually is a multiplication between a dim shuffle and a half normal. And what is a log P for a dim shuffle, right? In theory, it should be derived, but gets very messy very quickly.
Yeah. And that's pretty much what I meant just now. It kind of, if you start writing arbitrary graphs, that gets...
Exactly. Yeah. And importantly, the way that PyMC is working is that you work one variable at a time. And this is a bit limiting. We'll see later that the way we go in Apple is we treat the graph all at once, so we can ask these questions of constraints like, does this graph follow this shape, and can we be sure that we should give it this log P? For instance, one thing here you might notice, there's some ambiguity of what this x could mean. Is it a normal? For instance, you could have three interpretations. It can be a convolution of a normal distribution and a half normal distribution. It can be a normal distribution conditioned on a scale, and the scale is a separate log term, or it can be the other way, right?
Yeah.
And so what we do in Apple is we look at these, and we, based on what value variables you give, we say, okay, you are conditioning on these. Mm-hmm. So whatever is free is going to be random, and we're going to derive the random variable for that. But we'll get to there. Anyway, the issue here is the dim shuffle.
But then you have all those convolutions, right? And probably only...
We don't have any convolution implemented. The only thing we do right now is saying, okay, this is not a convolution, we can derive the log p.
Okay.
That
makes sense.
Yeah. Right, but here the problem in this PR I was doing is I get to these dim shuffles, and now, I could hack around, but it wouldn't be pretty. It would get very nasty very quickly. So we went to Apple, and the API of Apple is something like this. We just work with random variables on the back end, and then we have this fancy function which is joint log prob, to which you give a dictionary which say for each random variable what is the associated value variable. Mm-hmm. Okay, so in this case it's just a normal that has an inverse gamma as the scale, or the square root of the inverse gamma.
So the idea would be implicitly, if you were not giving one particular input, you would have to integrate in order to get log p. Well, actually what happens here, for instance, if you don't give the scale, in this graph, the scale is going to be stochastic. So every time you're going to evaluate the log p, the scale is going to be a random draw, right? So it's going to be conditioned on the random draw of the scale, and there is no log p point. So you would actually have it would be conditioned on a draw in each particular case. So if you were to sample lots of those log p's, you would then get an approximation to the integral of the actual.
Exactly.
Log p. Yeah. Okay.
But in theory, we couldn't.
Probably be useful for ABC stuff, right?
Yeah, it might come in. Yeah, in ABC, a lot of places we might
want to do something
work with.
But it's also good to keep in mind that if you get a log p, it might still be a random thing.
Yeah, right now it gives you a warning. You have to suppress. If the final log p has any random variable, it's going to spit out warning. There's still a random variable here. You can suppress it, but you have to do it manually. Exactly because we are working with deriving these things, and we don't want accidentally to have stochastic graphs if users are not expecting.
So far, this is the same as m.log p in PyMC3.
Yeah. So far, this is the first example. There's nothing. This is the one in the README. Right, but so input is we give a generative graph or random variable graph. You give value variables for those. Implicitly you're saying I'm conditioning on these value variables, and the output is a log p graph that takes as input the value variables. Okay. In between, what we are doing is we are massaging a graph we get so that it becomes easier for us to take out the log p. So, for instance, we are taking away that dim shuffle. We are pushing it down to the in that case, like to the parameter. So we are saying the mu and the sigma of the normal, they are the ones that are going to be dim shuffled. So now we are again working just with an addition of two random variables. Okay, so we have this kind of generic rewrites that basically make graphs easier to parse and to convert to the log p. So for instance, the dim shuffle, we have this dim shuffle lift that just puts a dim shuffle in a place that's more convenient for us. Mm-hmm. Okay.
So you remove it from?
No, so you can get the same result if you dim shuffle the arguments of the normal distribution instead of the output
to the value variables.
Yeah. So instead of being two normal the copy, like a broadcasting of the normal distribution, you just broadcast the parameters. Okay. Just because that
those are the value variables.
The mu and the sigma. So instead of having instead of broadcasting the normal, you broadcast the mu and the sigma.
Okay. So then you can broadcast. Or you do this lift operation that broadcasts the parameters, and thereby in the graph, then the normal and the next
are at the same
tensor are next to each other, exactly. And then you can apply the transform easier.
Yeah. So we do basically whatever rewrites we consider are not changing the fundamental graph and make it easy for us to derive the log p graph. And this is the big limitation that we had a bit in PyMC3 in V4 is that you are working with one variable at a time, the way the API is structured, right? Yeah. So this is a way that we just send all the random variables and let it work a bit, like digest it so that we can get a log p graph or something more interesting, right?
we could already do the basics of V3, but this will allow us to do some more interesting stuff.
But then are you not just, like, let's say the mu is another random variable, right?
Sure.
Then you need to lift that into the next...
No, right, because everything is going to come, it's going to end up at the value variable, right? The value variable is going to replace your mu. So most of these are, right, they are conditionally independent, right? Yeah. So the graph does not become crazily complex. Right. Everything only...
I see why that works for dim shuffle, but for broadcast...
So we have an open discussion for that.
Oh, okay.
It indeed is not true. Like, it's not... For broadcast, it's only valid...
Or broadcast later, then you add how much randomness you add.
Exactly.
Sense, right?
You can do broadcasting validly in some conditions if basically the size of the base random variable is the same size as what you are broadcasting it with. Then it doesn't matter. But if the broadcasting happens after, you should have the same random draw for all dimensions, yeah. Right? Yeah. There's an open discussion for that.
Okay.
What's the number? -5?
It's the order that these rewrites happen. Right, and then we have control over, like we can do some rewrite that just makes mixtures easier to derive. And then we undo that work if you don't want it for the other rewrite.
And the ink subtensor, do you have the same issue there? Or general indexing with broadcasting?
So...
Yeah, I think first indexing first.
I think we don't have any issues with index. Okay, we are thinking of indexing just as a sub-indexing and not expanding with the index. So if your index is larger than the original variable, it's the same as the broadcasting issue.
That happens a lot, right?
Yeah. So the thing at this point, what we don't have is a perfect, this log P is exactly about this generative graph. At this point, we have a bit more fuzzy where assume that you're just saying, I want this kind of random variable. I want a random variable that expands with the indexing, okay? What would be the log P for that, okay? As if the size didn't matter. So whatever you pass as the input size is the random variable you meant all along. Right now it's fuzzy, but yeah, there are these issues with shaping that we still need to deal so that it's actually consistent.
So for example, indexing where you expand the size, when you implement pretty much any regression, right? You're probably going to index into some predictor.
Sure, but that's not going to be a random part.
Okay. And then you use those values to get at your mu value, and then you put that into your likelihood, and that later you want to get the log P of the likelihood.
Sure.
And then in that case you don't want the indexing to be the randomness of the I don't know. Maybe I'm sorry.
So there's some issues with broadcasting. They are mostly issues of, if I generated this graph, all my samples would be 4. But what I'm implying by this rewrite is that I would get 4 different samples because I'm broadcasting the mu to 4. So it's like if it was a random normal with 4 mu's, which if you call eval is going to have 4 different values, right? Whereas if you do mu plus 1 random variable, it should be 4 copies of the same value. So this is a kind of issues we have, but they are not big. They can be worked out, and we can say this is the API. It's just a way of saying I want this kind of random variable, and not necessarily this has to correspond to the generative graph. Okay. But yeah, those are concerns that we are thinking about also.
Another concern, are there situations where this lift operation or the transformation can be sort of degenerative, like more computationally expensive than the non-optimized graph, so to say?
So the lift is only happening here as an intermediate step for us to get the log P. There's not going to be any, the end result should be the same.
Okay, also with respect to memory footprint and
because in the end you're going to have a log P graph that once you put in the ISRF function is still going to do the normal cleanup of dim shuffles to the right place, right? All these things are then cleaned up by the normal rewrites in ISRF, right? Which one of them is just put the dim shuffle where it makes the least computational effort, right?
Okay.
So these rewrites are not for optimization, they are for simplification for us. Right. Any other question?
So they don't stick around?
No, not necessarily. Yeah, no. in the end, you're still going to put this into a function, and the function is going to do all the normal optimizations.
They are intermediate in the sense that, okay, I have my original graph, then I run that stuff, I get the log P, and then I further optimize the...
Sure, because you get an output which is...
So if, let's say... So I don't know if that actually happens, but let's assume that there is a dim shuffle that I want to be... that at one place is better than in another computationally, so you get the same result.
So that you'll have to work with the return. You manually, the user, you're gonna get a Isara graph, and then you can do whatever you want with it. But we are not in Apple thinking about how to give you a log P that's very optimized. We are worried about giving.
So the issue is if I optimized it.
You should only optimize it after, right? Because we're gonna do whatever we want to make it easy to derive the log P. Any optimization you should do with the output of the log probe.
I don't know, but if I write the model in a way where I think about, okay, where do I want to have the broadcasting?
Sure. But you are writing the random model. You are not writing the log P model. So I'm not sure that you're gonna know where the broadcasting of the log P terms should go into. What you can do is you can write your custom more efficient log P term, and then just say, Isara, instead of using the normal log P, use the one I created.
But I mean, in many cases, I don't know. So how often would actually kind of model code that I write in a model, let's say part of a regression or something, how often would that actually end up in that machinery?
I lost you, sorry. Say again.
So I guess the question there is what parts of the model that I write, so I write some...
The idea is you write the random model, the one that you would write with numpy.random.normal. You write your generative model, which it can be your coefficients, like dot product of the coefficients and your predictors. The idea is you give a generative random model, and we're going to give you the log P model if you like the equivalent log P model.
Yeah.
Okay, that's the idea.
But part of that random model that I wrote usually ends up in the log P model, right?
Sure, like the parameter is mu plus 5 of the next random variable. Sure.
But maybe I don't want that the log P model does. So okay, all what I'm thinking about is that if they're aggressive optimizations or optimizations in the sense of, okay, I'm trying to simplify things, that those might influence part of the generative model that I wrote in a way that I do not want.
So they shouldn't, right? I mean, that means we have a bug. You gave us a random graph, and we are giving you a wrong log P graph because we transformed it to something wrong.
Not wrong in the sense of gives incorrect results, but it's much slower than what I
that we can, and that we are not giving guarantees about that. That we're saying you have the log P graph, now manage it. If you want to optimize, it's on your hand. Okay? You can do all your graph rewriting if you want on top of that. You can look for the patterns that we took away and put them back. You are free to do whatever you want after that.
Yeah, I get that. Once I have the graph, I can do optimizations on the graph. But usually, if I optimize something, I don't optimize the graph afterwards, but I think about how do I write the model in the first place.
But would you optimize the generative model? No, you would optimize the log P, right?
But
you don't think in the generative model, you don't think about what transform my value variable is going to have. That's not part of the generative model.
I know usually that large parts of the generative model will just end up 1-for-1 in the log P.
Yeah.
So I know that when I write the generative model, I know that stuff that I write will also end up in the log P computation. Mm-hmm. So while I write that, I can think about, okay, in what order do I want things to actually happen? Where do I want to have broadcasting, for example?
Yeah.
And I usually think about stuff like that when I write
so
generative models.
That we are rewriting.
Later step in the pipeline to just undo all that and make it simpler.
So
I guess, Adrian, you're right thinking about these optimizations when writing the model already. So these simplifications will make a big change to your models in those cases. But for a lot of users, I wouldn't expect people to already think ahead about how is this graph going to be optimized, or how is this
a power user
computational graph more efficient. But I completely get your point of concern about optimizations that are less than ideal. So a question towards Ricardo then, is there an API in APPL where you could say, okay, this is the array of optimizations that were being applied to this model, and I want to turn these off.
So these to benchmark them against each other. You have this RV syncing the database. This is a standard one, and you can just go and say, don't use this rewrite.
I mean, maybe what I'm thinking is probably is going ahead of things a little bit, but just think it's useful to keep in mind that simplifications that might make a log P easier to work out might not necessarily be a good idea in general, but to be a bit conservative in what optimizations you do on the graph, and just thinking about, okay, I don't want to make it worse. So if somebody thought about, I write it this way because I know that that's the better way, then you probably do not want to destroy.
But then I would say probably you don't want to use Apple. Then I would say probably you already, I mean, you are at the point where you can just write a log P graph yourself directly, right? What are you taking from the library?
It's just unintuitive.
The point here is that you don't think about those things. The point is you have a generative graph. We're going to give you a log P graph, which is going to have the output is going to have the general optimizations that Arizara has, and it's probably going to be more efficient than what you would write naively by hand. Okay. What we are doing at this point is not any of that. It's just okay. I mean, if you give us a standard one that just has random normal, half normal, everything as a distribution, you're going to get the same. None of these rewrites are going to apply, right? You're not going to have broadcast that much or nothing like that.
Can just go on. If we find corner cases later where we figure out,
and we can open an issue immediately. So that's the trick. So we're going to rework a bit the graph in the middle so that we can more easily extract log P terms. So what things can we do already or almost ready to do? We can do the thing I was trying in the PR in PyMC3. So in this case, we have a random variable as a base, and we are multiplying it by a scalar and exponentiating. Okay, and this is going to be our value variable. So I'm going to give values as input on this scale, and basically we're going to back transform it so that in the end we can put something into the normal log P and add the right Jacobian term of the exponential transform. Okay. So actually, it passes this test. This graph is exactly equivalent as if we just call a log norm. Okay, so these are the kind of, so we have these scaling and location shifts, exponential and logarithmic transformations. Thomas went closer.
Okay, so I was gonna ask something. I mean, I remember once when we were talking about ARIMA and all those time series models, and I remember you telling me that the generative part of the model should be in synchronization with the log P estimation part of the model, like the random and the log P functions. But like that works fine for regular statistical distributions. But say you have a time series estimation, so the way we generate those processes and the way we estimate those can often vary a lot, because it is because they are not distributions at the very core. So ways to estimate them often vary, and like if you try to just do a backtracking way of the generating thing to estimate, that often falls out and goes very wrong. Like you'll use Kalman filter and stuff like that for estimating the log P, but for generating you can just do a simple convolution, so like scipy dot filter. So how does that sort of work in Apple? I mean, I'm just trying to understand.
So you are asking a question that's a bit ahead of the point where we are now. So you are asking, can we do things other than just give you the crude log P graph? Can you also, figure out that, this is a Kalman filter, and then you can give a much simpler expression? which you'll be able to, it will also be easier, right? We know that, for instance, we have this convolution of normal distributions. We can have a rewrite that says, maybe an optional one that says, okay, treat it as if it was a common filter, whatever. Okay, so
maybe
we don't have at this point, but you can convert some random graphs into simpler log P graphs that are not just one by one.
So an easy example would be, let's say you have two random normal distributions and you take the sum of those and you want to get the log P of the sum. Well, you can just work out the log P directly because you know that the sum of two normals is different.
Exactly. Which we can go two ways. We can go to work on the log P graph, or we can say in these intermediate steps we can replace those two normals by a normal with the mean and the sigma. That would give you the right log P. So we plan to do these kind of things. They are not yet, but this kind of non-naive, that we know mathematically they are equivalent and they are much more efficient. We can also do, because we have the graph and we know there are two normals there. Let's just consider one normal with the mu, the sum of the mu's and product of the sigmas, or square root of. When you do a convolution of the normals, what happens?
Variances add up.
The variances add up. And the means also, right?
Okay, so I was thinking maybe something like, we just use Apple for the log P part, and maybe like in the default API, it will try to use the generative part as something that's similar to the log P part as well, but we don't use that. Even if it's generated,
so just, in theory, you would just have to write the generative model. What you might need to do, so you just write the random model, and in theory, Apple is amazing and it's figured out your log P for everything. What you might need is then you're going to have to add your custom rewrite that gives you the kind of log P you care about, the efficient log P you care about.
Yeah, because generating ARMA or any of the time like for the whole category of time series distributions, generating a random sample is not something that's very difficult, and it is not even something that's very useful, because usually it's for estimating existing distributions, because it's not exactly a distribution that you want to generate and use. So
Alex is making a joke, sorry. Because a gardener just passed and he was saying it's max.
So we can just like sort of do the generating part manually, and assume that the log P graph is what, like we will use Apple in a way, assuming that the log P part is the generating part, create the graph accordingly, but then we don't use the generating part and only the log P part.
You use the generative for predictive sampling and stuff like that, but depends what you want to write. You in PyMC3 you can also use the generative graph if you want to do random predictive sampling.
But for generating you can just using NumPy or SciPy
sure, but
a custom thing would be faster.
So but the idea is exactly that. It's easier for users to think about the generative graph even in NumPy, and ideally you just replace NumPy normal by ISR random normal, and you get still the same generative graph, but now we can also automatically derive for you the log P graph, including for these weird cases with time series that you are mentioning. But obviously we need to do some work so that we get what we want out of the log P.
For time series, it won't really happen automatically. There'll need to be quite a few tweaks.
I don't know. So that's not a part I'm working on. I have one example, and it's going to be a group work example to find out what Brandon model means with a scan. So we'll get there.
So I saw this time series issue that I think Brandon created on SRA that Kostik sent me a while ago, that like about the joint log probability for like sort of customizing all the time series distributions. So let me know like what's going on with that, and I can help with that, because I want to get the time series stuff started up soon. So
sure. Let's see if that slide also brings up anything. Okay. So this is. Everybody is on board with this? No issues with broadcasting? You agree that the log P term is correct? Okay. So we can do, I'm working on this, it's almost ready. We can do clipped variables.
Mm-hmm.
Okay. Does anyone know what should be the log P?
No.
For this kind of variable? This is a quiz.
Yeah, I don't.
does it also work if the right or left bound is a variable as well?
Sure.
So the derivative of that is taken into account.
Yeah, sure.
So you just
it's
have
a
to
truncated normal, right?
No, censored.
Censored normal. So
Okay.
Because everything above the edges becomes clipped, right?
clip.
Okay.
Yes.
Everything that -2 becomes a -1.
Yeah.
Whereas in truncated, you just lose those
Yeah,
observations.
you just don't see them.
So,
Okay.
but you need the CDF for that.
Mhm.
And you,
And that's what we do in the backend. We plug so the log p term for this is going to be the normal base plus the CDF plus some if statements. If something is -2, then it's negative infinity. You could not have observed -2.
Yeah.
Right?
that's wild.
Mixtures with indexing, they are working. They were one of the first things that were put on by Brandon. So right, we have a normal, a gamma, we stack them in this MRV and we index it by the Bernoulli, right? And we can just ask for the joint log probe of this.
That's insane.
Okay.
maybe something that might be cool is if the joint log P were more explicit about what is marginalized out.
So at this point, nothing is marginalized out. Everything that stays is random. Everything you want to condition, you give a value variable. So in this case, the I is going to be random, but you could just as easily say, I want to the index random variable to have the index value variable.
Wait,
I.
okay, I thought the mixture was marginalized out, then I don't understand.
In this case, it's not marginalized. In this case, it's going to be a stochastic graph where the index is stochastic. Every time you call it, you have a random draw from the I. So the log p term is just of the...
Okay, so I think I would really like it if that was explicit in the joint log prop. That I explicitly
You have a
say-
warning now, because you have a warning saying the Bernoulli is still there.
You could have a keyword argument that explicitly says those are random variables.
Okay, and so what we have...
Those are stochastic.
So what we have so far is, basically here, this is just an example. I don't know where I copied, but the real example also has the index value variable. And what we're implying is whatever you are giving as a value variable, it's basically everything that depends on it is conditioned on it. Everything that you don't have a value variable, it should be a marginalization. But we are still working on that.
But it would be really cool, I think, if that was really explicit. Just you have to mention all variables somehow. And if you do not mention at least one variable, then it just throws an error.
Sure.
I
Let
think
me
that
see
would
the
make
example.
more sense.
I open an issue example for convolutions. Let me see I will show you and then you see.
And I think if you have that with just a random index, I think that Bernoulli, for example, that should be fairly easy to marginalize out as well, right?
Yeah.
I mean, that's just the...
Yeah, right. You just add up the two possible I's.
Yeah.
That's something else that we are working on.
Yeah.
But yeah, so it's still evolving
If you really make that explicit and just say what log P is it actually, and it doesn't
it should be
depend on what
definitely.
What your graph is.
So the way it should be is that this API already changed, so it only actually has a dictionary. It doesn't have this first MRV anymore. But what it should be is like the first dictionary is conditioned on, the second dictionary should be marginalized this variable, and then if something is not in the marginalized and not in the condition, then it's either random or we should fail.
Or just have a third thing, those are random.
Sure. Yeah, we can be as explicit, sure. So that there are no... I agree that we don't want surprises because we are doing a lot of magic behind the curtain.
So the reason why you think this should be marginalized out because it's not showing up in the joint log problem?
Yeah.
Okay.
So if it's not mentioned, I would just have assumed it's marginalized out.
Right.
Yeah, and
But
it's
if
not.
that's an explicit argument, those are marginalized out, those are random, and we have the log P of those.
Yeah.
Those three things. If you have those explicitly, and if something is missing, then you just say, okay, no, something's missing.
Exactly.
Yeah. So why is that? So would that be working, or is that actually?
That's working. It's just the I is going to be a random draw every time you call log P.
Okay. No, I get it. Okay. So that's what you mean with stochastic.
But this is a silly example. The examples we're actually using are also giving the index, obviously, as a...
So if you vectorize that and took the expectation you would actually get in the limit, you would get
Sure. If you call it many times, it would be the well, but it's not. It's just it's the log P of M, right? It just doesn't have the log P of the Bernoulli, because in this graph we are not computing. There's no Bernoulli log P, so it's still a valid graph. It's not a marginalization of both M and index. It's just, index is, in this case, you can think of index instead of being a scalar you are giving it, it's a random scalar.
Yeah.
But has no log p term attached to it. So what you get of evaluating the m many times is just the probability of m. You never have the Bernoulli probability there.
But if you call it many times, then depending on p,
it's never going to have the effect of the Bernoulli probability. It doesn't matter if the p was 0.9 or...
Wait, okay, maybe I'm still not getting something.
This is a silly example. This is not the best example.
So what is a log prop that has a stochastic term, and every time I evaluate, I get a different result?
Yeah, it takes one. So it's what we use in ABC, for instance. Right? Every time we call ABC, it's a random log. It's a different log p.
Yeah. Okay. So we default to.
But with a warning. We default with a warning, right? There's a random variable still in the graph.
You're saying we should always be explicit. What do you want?
Yeah. But where does the p here come from? I'm not getting that. That's.
Sorry, which.
So the p, not the index itself. The index is fine.
Sure.
But the p is a scalar.
Yeah, it's an input.
So that's not random.
Yeah.
But it's not specified anywhere, right?
Yeah.
Also,
well, we are not evaluating anything here.
P. So it would be if I want to evaluate.
You would need to give p.
Constant.
Yeah.
Okay.
You need to give p.
Okay. No, okay.
So in this example, you could just have used, 0.3 for the p.
Sure. Yeah.
And just to check if my understanding of this is correct, if let's say we put the 0.3 for the p,
Mm-hmm.
And now we want to run MCMC.
Mm-hmm.
Then we would only have 2 dimensions. Would we have any free variables there?
Yeah, you have the m, right? Unless that's observed.
Okay, let's keep this p.
So everything that we have a value variable is what it's a free variable in normal MCMC, right? This m is what Nuts tries to figure out, right? Is what it changes in every step of the algorithm. Changes m and c.
Actually, when you want to sample, you would also add x and y there, probably.
What x and y? No. Those are not part of the final graph, right?
No.
All right.
Those would be the parameters that you want to infer, probably.
No, those would be the components of the mixture, right? They're just basically saying what are the mixture distribution.
Yeah.
You could infer them, but then you also have to give them a value variable. But then the mixture is deterministic from condition on the components. The mixture is deterministic.
So what even is the log p for this? So what do I input? So
I should change this example. Yeah. So the log p of this term is going to be so the input.
But now I'm making
In
the
hindsight,
inference that it was the warning for the battery.
It's the one that takes a long time now to turn on.
Huh. Yeah, exactly. Huh. So it's not on that? Oh, yeah, okay.
But yeah, if that works for the Bernoulli and maybe also some other discrete variables, that would be really cool, I think.
In the marginalization. Yeah, that's what we want to do. So it works already, the explicit one, like you give both the index as a value variable and the mixture as a value variable.
Yeah. And I think you need, if you want to sample from the marginalization and then reconstruct the p-value, for example.
Yeah.
Back.
So if we can do that,
because
without always having to write that marginalization.
Yeah, exactly. Because when you do mixtures, then you marginalize, but then having the.
Du kannst auch den Laptop, den du hast, vielleicht so richten, dass ich den Fernseher oder was ihr da habt sehe.
Wieso? Das hat doch funktioniert mit dem Ding, oder?
Final discrete distribution is okay.
Yeah.
But we might also want to do some fancy, convolutions that have closed form for, marginalizing some continuous distributions, or even approximating discrete distributions with infinite support. So that's the idea. There's a lot of knowledge.
It would also be interesting if we could, for example, use numerical integration to...
Yeah, I suggested that too. I think we could do as a first step.
So in the Arisian project, for example, we are doing that.
I think you showed me we had one hackathon where you...
Yeah. Right.
Was it the splines that we were integrating, no? Yeah.
Right. Because I think that's probably something that would be useful in more projects as well.
Integration is a tough one to implement as a ISR operation, because it's one that has to have access to the whole graph, in the sense that it's, the kind of inputs you need for integration are a bit weird. You need the final compiled
function in a sense, right?
So it's kind of a weird
self-referential. Yeah, I know what you mean.
I think I read there was someone on Stack Overflow that suggested something.
For example, the same problem is with ODEs and stuff.
Yeah.
So that happens definitely.
But it would be very cool if we could.
Okay.
Is the meeting up?
Yep.
Cool.
You can hear Michael, right? And see the screen.
All right.
So
okay.
There was a break here for alcohol.
Yeah, I think I got this thing with this. I had a misunderstanding that I think that one was resolved. So.
Yeah, I'm sorry for this example. I will one day update the slides and give a reasonable example. No, Thomas is going back to it.
Yeah, well, we can...
No, sure. Okay, so what this does, this m log p, is a function that takes as input p and the m value variable, right?
And that's a scalar.
P is a scalar, m is going to be a scalar in this case as well.
Yeah, okay.
Yeah. And it's going to give you the log p term of m, and the index is going to be a random draw.
Yeah.
Okay. And it's not going to have any Bernoulli log p term in this case.
Okay. So sometimes I will input maybe a positive value, and by chance I get the draw from this one, and then it will evaluate it to the log p of this one.
Yeah, exactly.
Sometimes it will evaluate to the log p of this one.
Yeah.
Okay, got it.
In the more reasonable case, the index is also something you are inferring, so it's also one of the inputs, right? And then you say if index is 0, and then it has always to come from the left mixture, and then either it's a value that's compatible with that or very unlikely.
So what are actually the most important ones of those? So I guess marginalization of Bernoulli stuff.
And the categorical?
And categorical, then...
And that gives
more
you...
important than clipped is probably truncated.
Yeah,
and
but that I have to create a new operation. There is no standard operation that's equivalent to truncation. Because truncation requires you to redraw.
You have to redo it, yeah.
Yeah.
And...
So let's continue the list. We are going. So we have scan graphs. I have no idea what this example is doing.
But scan graphs, I guess they are neat, but I'm not sure if they are the most...
They are very useful for Markov models.
Yeah, I think it's...
You cannot do that in PyMC3 with the basic API at all, because you cannot create random variables inside a loop.
Yeah.
Right, you cannot define a loop where you just go through the indexes of.
You have to do it manually in a custom op or something.
Yeah. Exactly. But there's no reason why we can't do it.
This example has Brendan written all over it, right?
Yeah.
He had a description. It's something like it. So the output of every step of the loop is a random normal that depends on mu, and mu is a combination of a deterministic offset of 1 and the value of mu before.
Yeah, it's an autoregressive.
Yeah, it's with offset of 1, constant offset of 1. Right? And we derive the log p. It's not completely worked, but idea is, this is a straightforward log p term to derive. It's something we couldn't do in V3 at all.
But how is this different from a random walk?
It's not.
It's not different, yeah.
But the idea is you can have any kind of random walk. You can have a plus, can be another random variable.
Yeah, and you can also have different autoregressive terms.
Yeah.
Like you don't have to use only A or 1.
Yeah. And again, it's a case where the generative graph works as the generative graph you'd expect, because you are just this creates a autoregressive random walk, right?
And then we just transform this into a log P graph. Right, so this is something that's very easy to do in Stan, because you can just do a loop and say, basically that code inside, you can write it as a Stan loop, but you couldn't do in PyMC.
But I mean, the same way as it works internally in Stan, you could do it in PyMC and just use a Python loop that gets unrolled.
But we cannot work with loops and...
Just
so for instance,
Python loop where you define new variables. Isn't that pretty much what happens if you do loops in Stan? I think they get unrolled.
Sure. And here it's getting unrolled. What we cannot do is use Python loops with just, old pm.normal, right? Because pm.normal is doing a lot of magic under the hood. You cannot create a normal variable with a name in a loop. You can try, but you cannot. I don't know what error you're going to get. You're going to get some error.
You mean with the same name?
You couldn't create a
V3
PyMC distribution inside a scan loop. Just doesn't.
No, not in a scan loop, but you can have it
in a Python loop. And then you can append, but then you have very quickly get to a recursion limit. Yeah. You can do 128 variables, and that's the maximum random walk you can make.
Oh, really?
Yeah, there's the C code has a recursive limit of like.
Oh, that's funny. Okay.
Yeah.
I didn't know that.
Not the C code actually, the indexing, still pre-C.
Okay, so we need this.
Yeah, we need this. This is
just to clarify again, we can have random walks in PyMC3 also by doing things like cumulative sum. But if we want to do more fancy things where it's not looking at the latest value, but maybe at the last three and doing a weighted average, that would be a case for the scan. And I think there's actually something very similar to this happening in the RT Live model, isn't it? With the convolution that is implemented in a scan.
That I don't know.
Yeah, Junpeng did that.
Yeah, there's a very very fancy.
Yeah.
And I mean, you can always just have a custom op. I mean, that's always.
And what we can do here also is, we can, in those rewrites, we can canonicalize a scan that's equivalent to a CumSum and just transform into a CumSum.
Yeah.
Okay? If that gives a more efficient log P, for instance, which it does, then because this log P is going to have a scan, right?
Yeah. You can't have a scan inside a custom op, can you?
No, you just don't do a scan.
You do a Python.
You just do a
Python loop. You can do anything.
It would be super slow, right?
Yeah.
No, it won't be. I mean, you can do a number.
For civics, we did a Python loops, but in number, and we parallelized it, and we got some nasty.
But then you tie to backend, right? This wants to be backend agnostic.
Yeah. And it also wants to benefit from
gradients than yourself, which is
Yeah. No, I mean there is no arguing that V3 is very weak for time series stuff, anyways. So I mean, any improvement on that is welcome, I think.
Yeah, I think this is going to be a big game changer.
Yeah.
So this is me throwing one at saying like, hey Brandon, what do you think? Can we work on this? So we could have order statistics. Okay. We just need to work with cumulative distributions, right? Do some magic with that, so that now your variable can be, the max of 3 variables, right? Stuff like that. Anything that the textbook, we know the textbook solution to derive a log P for simple expression, we can do the magic here.
Holy shit.
CumSums is Alex is going to work in this retreat.
Ah yes, true.
Would be something like this, right? So this is the different way of doing a time series, the one that PyMC3 has, the normal random walk, right? Where we stack an initial random variable, in this case a gamma, just so it's different, and then a CumSum of some other random variable. For instance, a normal with 100 time steps that you cannot do with a for loop, right? And we can derive this log P also. It's something we know how to, how to solve for.
That would still qualify as a normal random walk, right?
It would, but you could, and then you can have any, but now you are not constrained. You can say anything can go here as long as it's something that makes sense with location shift. And and the scaling can be also.
I'm doing this all the time, and it's really hard to sample sometimes. So you're saying this can be optimized and be more efficient than what you currently get with V4, V3?
No. So
I mean, the code you see here, this stacking to RVs, you can basically do that with version 3.
Yeah, this you can. This is not new. It's just now you're going to have flexibility. You can put anything into Sigma. You can put any combination of initial value and you can have 3 cum-sums. You can have, a stack of a third cum-sum that comes after. Maybe then it becomes, a student distribution after the first year. It doesn't matter.
And if you have trouble sampling something, and that is probably more a parameterization issue than a
mathematical
issue, I guess.
Numerical. Right, so something you can do, and then obviously truncated variables. That's what we have in mind for this kind of derived random variables. I think that's all. Yeah, and then we plug it into PyMC3 and we get all the nice PyMC3 API. But now we also tell people you can do these weird things, and ideally what we're going to have is something for these derived ones where you just say pm.var, right? And you put an arbitrary expression there. So your pm var can be a scan, right? Yeah. Give me, this is my model variable, it's a scan.
Yeah, you have submodels, basically, right?
Yeah.
So something that's a bit agnostic. Yeah.
Cool.
And that's it. This is the final slide.
Wow. That
cool.
Was really enlightening.
You guys excited?
Thanks.
Yeah.
Yeah, I mean, I wanted to sleep during the presentation. It's not because of you, it's just because I didn't have a lot of sleep. The presentation was exciting.
And it has a great logo.
Yeah.
It's just something else.
The name sleep too.
Yeah. Why is the E in brackets?
I have no idea.
Okay.
I have no idea. Yeah. I don't know if it's to make it
I have a logo idea that maybe it doesn't clash with copyright problems. If you take the seeds of the apple and make a logo out of that in a way that people can still recognize, or maybe in combination with the name that these are apple seeds, then this is like the core and the seed in the PyMC3.
Ooh. Or you just take the apple seed.
And it's not copyrighted.
Umlaut.
Yeah.
And how is Google gonna find it?
Yeah, but I think the AE is for Esara, right?
Yeah. So it might be that the AE was for SR and the E is taken out, so it's pronounced apple. Is that the logic? Were you
maybe,
informed about this?
No.
Otherwise,
I will ask Brandon. I have no idea.
To me, what would make more sense is to have AE in brackets. Because it's Esara plus PPL, stuff like that.
So we can ask Brandon now.
Yeah.
Cool.
Okay, so that's fascinating.
Right.
And a lot of things make sense now.
Thomas is illuminated. So that's it. What we don't have working that we really need so that we can, we could plug this in PyMC3, except the only thing we don't have yet that we really want both for V4 release and, generally is these discrete mixture distributions, right? So that we can generate the graph that goes into Apple can still have the explicit indexes, but we want the log P, most of the cases we want it marginalized out. The cool thing is if you implement that for this specific case, it's going to work for any kind of discrete variable.
Yeah.
So marginalization, is there a PR for that out there, or?
No, Remy said he is interested in working in it. Remy, but no, there's no PR yet.
That would be amazing. Yeah.
That would be very cool.
So what I'm still a bit uncertain about is how the whole transformation stuff.
I can show you that. I don't have slides here. Can I put a tab there, a normal Google tab?
Okay.
It kind of feels like with that way of thinking about the log P's, you should be able to do a lot with transformation.